So yeah, so IR is used to identify function groups, and mass spec, it covers the same thing. It has the same type of style in how they can ask you questions, where they have the same, 3 mass spec graphs, fill in the blank, and then so all of these are going to be like, for example, like C5H12. Okay, so C5H12 can be written, or it can look like this. It can look like that. It can look like this. Okay, and yeah, so different mass specs are going to have different cuttings, and based on those cutting of the fragments, you're going to match them to the graph. Okay. So they can ask it like this, or they can ask based on just they'll give you the graph, they'll give you the formula. So let's say C5H12, and they'll tell you, okay, I want MZ or M plus value of a certain number. Okay. And then you have to draw the fragmented compound in the box. Okay, so using the formula and using the graph, you have to put together your compound, and so there might be another box where they say compound A, where you have to draw it, and then from that compound you might have different fragments. Sorry, this should be MC. Okay. All right. So, okay. So, any questions on like the format of how you'll be asked? Okay. So, any questions on mass spec in general? Okay. What's giving you guys more trouble, mass spec or IR? IR? Does everyone agree, or is mass spec giving you more trouble? Mass spec? Yeah. What were you gonna say? So, for questions like this, are you talking about like when there's like a fragment here and then you're left with a positive charge here? So yeah, anytime there's a positive charge underneath the OH, it is going to be resonance stabilized. Okay, sorry. There's a third way that you can actually be asked this question that relates to your question. So it can also be a ranking question. So you have 5 fragments, right? And you have compound A, and between compound A, they'll give you 5 different ways. Okay, from 5 different ways, the first criteria you're looking at is the compound stabilization, so the carbocation stability. And then if the carbocation stability is equal, then you have to look at the fragment stability. So the fragment will always get the radical. So compound A will have the positive charge, and that's resonance 3, 2, 1, and then the fragment will have the radical, and that's again also 3, 2, 1 with resonance. Okay, so this is 3 different ways they can ask it. But yeah, if there's a positive charge underneath the OH or some type of oxygen, it is going to have resonance. So you should look for those first. And for the ranking, when they actually give you the original compound, they won't tell you all the different fragments. You actually have to Actually, no, it's the other way. They'll give you the 5 fragments, but you have to put together the original compound. Yeah. Yeah, let me look for an example. But before I do that, do you guys actually want me to cover the quiz, the practice quiz? Or do you guys have any specific questions on the practice quiz? Okay, I'll quickly go through the practice quiz to see if there's any questions on it. Give me 1 second. So let's look at this first. So anytime they give you this, I had this exact same practice quiz also when I took it. So the N plus, the rightmost fragment on your mass spec, that's going to be your total compound A like mass. So 121 is like the whole value of it. Okay. So 106 and 77, those are your individual fragments. And what you should, like the first thing you have to do when you get this problem is, okay, there's 2 different things. You can either look at the mass spec or you can look at the IR, and I'll show you different ways. So looking at 121, you want to take whatever the N plus value is, and you want to subtract all the different peaks that they give you. Now in this case, they gave you 2 peaks, 106 and 77, but sometimes you can, all of these little tiny peaks, you can also subtract that and also get different fragments. But they give you these because it's easier to spot out, and it gives you the puzzle pieces much quicker. Okay, so 121 minus 106, and so 121 minus 106. Does anyone know what that is? 15. Yeah. So does anyone know what molecule is 15? Methyl. Okay. So it's going to be a CH3. And there was also 121 minus 77. Okay. And 44? Yeah. Okay. So the 44 isn't the important part. The 77 is the important part. Does anyone know what 77 is? Right off the top of your head. Yeah, benzene ring. Okay. So these are the certain things that you should probably know. 15, 29, 43, and 57. These are your methyl, ethyl, propyl, and butyl. And the reason why, not necessarily memorize, but you can think of it that way, because knowing these numbers right off the top of your head will help you get to the answer quicker, because time is a huge issue on this exam, because there's different graphs and different things that you're trying to piece together, and it's a lot of trial and error. So there's no clear-cut answer like a ranking question. You actually have to put together a compound from scratch. Yeah. No, that's a butyl. Benzene ring is going to be 77. And that's a benzene ring with like some type of substituent on it. So that's 6 times 12, and then plus 5 hydrogens. Okay, that's how you get 77. Okay. So in our problem, M plus was 121, and we had to cut out a methyl for 1, so 106 and 77. So we're cutting out a methyl for 1, and we're cutting out a whole benzene ring for the other. Yeah. No. I'm saying it's like, you're talking about this, right? It's the ring, but it's a ring with like a compound. No, it's just the ring. What I'm trying to say is that that hydrogen on that where the compound is, you don't count it because there's something else attached. That's why if it's just a benzene ring, it's going to be 78. But usually it's a benzene ring along with something else attached to it. Okay. All right. So let's go back to our graph. So right off the bat, you should know that there's going to be a benzene ring in the problem, and obviously methyls. So what this graph tells us is there's three different locations you should look at. So look at the I'll redraw it right here. So 1600, 3000, I think it was about 3400. Okay, so pretty much on all your IR graphs, you're going to have peaks that look like this. So all that is just CH bonds. Okay, it doesn't really tell you much. But if you see a peak exactly at 1600, that's another confirmation that, okay, it's going to be a benzene ring. Okay. So this is a benzene ring, and we know that there's a couple of CHs. Now at 3400, there's also that sharp peak right here. Okay. Now a peak at that range, that value, and if it only has a single spike, does anyone know what that is?
Secondary.
Yeah. So at 3400 or around 3300, if it has spikes, it's going to be a mean. But to know if it's primary or secondary, you have to look at how many spikes there are. So for secondary, there's going to be one spike, and for primary, there's going to be two spikes. So it's kind of inverse. Okay? So because there's only one spike, we know that it's going to be a secondary amine. Okay? So let's put together all the different things we know so far. So there's a benzene ring, and then there's a secondary amine. Okay? Now, so if you try to add that up, so benzene ring is what, 77, and then a secondary amine, just the N and the H, that's going to be another 15, because nitrogen is 14. So that's 92. So 121 minus 92, that's going to be 29. So what did you say 29 was? Ethyl. Okay. So this is like how you get the remaining pieces. So there's going to be an ethyl. Okay. So yeah. So all three of these groups will add up to our M plus value. So all we have to do is just place it together. Now we just have to see which order we're going to do. So with the benzene ring, you could either do the ethyl first or the amine first. Now obviously, looking the way we set it up, we realize it has to be the amine first because it's secondary. But if you didn't know that and you tried to do the secondary, the ethyl first, and then you try to put the amine, it doesn't work out because that's a primary amine. So this is with ethyl and then amine first, amine second. This way is amine first, and ethyl second. Okay, so this should be your answer. So that's your secondary amine with the benzene ring and the ethyl. Yeah. Terminal alkyne as in like C to C or C to N? Like that, right?
Mm-hmm.
So I believe these are only at like the two triple bonds you're usually looking at are only going to be at the 2200.
Mm-hmm.
So like you're not looking at 3400. Are you talking about the other one? They might give you the range like single bonds, double bonds. Like it increases IR as you go up, but you're not really looking at triple and double. It's mostly going to be the more obvious ones. But for the only range you have to look at for triple is at 2200. So if it's past 2200, there's a spike here and there's a spike here, the left one is going to be nitrile, and the right one is going to be a C triple bond C. Okay. Yeah. But it's, yeah, like you said, there could be many things around that area, so you do have to like double check and trial and error, and that's why mass spec comes into play. But because you have a certain number of mass you have to reach. Okay. All right. So, second question. Okay. The first question is just benzene ring and the amine secondary amine group. Second question is just putting together the compound, which we did right here, and then the third question it says 106 and 77. So now that we have this, we can cut exactly a methyl. And anytime you cut, you're cutting through bonds, okay, not through atoms. So we're cutting through right here for the 106, and anytime we cut it right there, the positive charge is going to come right here. Okay, so it's important to like realize how many like hydrogens are on each carbon. So originally this had 2 hydrogens, right? Now this only has 1 hydrogen because one of the other hydrogens got replaced by the positive charge. Okay, so this is your 106 fragment, and then your 77 fragment. You're cutting out a benzene ring, so you're cutting right here. So all you're left with is, it should look like that. I haven't looked at the answer key, but yeah. Wait, actually, sorry. So 77 is what? Yeah. You should be left with a benzene ring. With a positive charge on one of the carbons. Yeah, either way, you could either do that and put the positive charge outside and a radical next to it, or you can do that. I think either way you should get credit. And then why is the fragment 106 the highest abundance? Okay, so the reason why this is the highest abundance, because this positive charge can resonate with the nitrogen right here, and then it can then resonate with the benzene ring. Okay, so anytime you see the highest peak, that just means it's the base peak. It's also called the base peak, and that means it has the highest abundance. So all that just means that it's the most stable, like, carbocation base, and so that usually means there's resonance involved. Okay, but other than that, like other than for like ranking and stuff, you don't really need to know what's base peak or whatever. Yeah. Any questions on that so far? So we've done all of number 1 so far. Okay. So was that too hard? Too easy? Alright. So this is actually a little bit easier. So C6H13 bromine. So you can actually get the answer in 2 different ways. You can get the answer either just by following the reaction through, or just looking at the IR graph. Okay. I'm gonna do the first way, just following the reaction through, because that'll help you prepare for the quiz through knowing the reactions. So. Okay. So. So C6, H13, and bromine. Okay. So it says, so I'm gonna draw out the basic structure by just putting 6 carbons and then putting a bromine at the very end. Okay. And the H's should match up. Now it's saying this went through NaOH, so that just replaces the bromine. Okay, this is just SN2, right? This is your leaving group, and that's your nucleophile with a negative charge on the OH, and then it just attacks it. Okay, so that went through PCC. And do you guys remember what type of reagent that is? Yeah. So it's an oxidizing agent, and between strong and mild/weak, it's going to be the weak one. So weak oxidizing agent, and you have a primary alcohol. What is that going to create? An aldehyde. Okay. So the aldehyde is going to be on this carbon, and then an H right there. Okay. So it's saying compound C. So this was C. And this was B, and then this is D. Okay. And the first question is just to identify what compound D is. And compound D should match the IR graph. Okay. Now, you can technically get compound D just using the initial formula and the IR graph, because if you look at the peak right here, you see it's around 1700. You don't know exactly what number, and they won't tell you exactly. I mean, they might, but sometimes they're not as nice. They won't tell you 1715, 1730, or whatever. So there's additional rules that you have to look out for. Not rules, but patterns on the graph. So you see these two little peaks right here. So that's around 2700 and 2800. Okay. So if you see a carbonyl peak right here and two little spikes over here, that tells you it's an aldehyde. Okay. Now, if there's no peaks right there and you see a little overtone, I forgot exactly where, but overtones will tell you if it's a ketone or an ester. Okay. But like these are different ways you can see if it's which carbonyl it is. Okay. But for in this case, just following through the reactions, and these aren't difficult reactions. Like this you guys learned in last year, and this should be the most basic one you guys learned. It's not too difficult, so that's why it should match up to this. Okay, so let's look at the next question. But any questions on how I got compound D? Okay. So it says the mass spec of compound D has a fragment of 44. Okay, so identify the fragment. Okay. So 44, they didn't tell you the total weight of this, so you can either calculate that and then subtract 44 and then get your answer, or you can just add up 44 in terms of atoms. Okay, so I'm just gonna start somewhere. I'm gonna start with the aldehyde. Because 44, it doesn't match up one of our 15, 29, 43, right? But 43 is very close to 44, right? So that means it has to do something with that. So let's say, there's a carbon. Let's say if we cut right here, okay? So there's a carbon, oxygen, and a hydrogen. So that's what? So that's 12 plus 16 plus 1. Okay, so that's 29. Okay, so 29, it won't cut it. So let's add another carbon. Okay, so if you add another carbon to it, so that should be another 14. So another 14 is going to get us 43. Okay, so 43, and we're one off. So do you guys know what we should do when we're exactly one off? What? Double bond? Yeah, I was thinking McLafferty rearrangement. So I think it should be. So do you guys know what McLafferty rearrangement is? No? Okay, let me show you that real quick. So usually you should have a carbonyl and 3 carbons right next to your carbonyl, where the first carbon is alpha, second carbon is beta, and the third carbon is gamma. Okay. Now the rearrangement occurs like this. You're going to rearrange the gamma carbon to be right next to the oxygen. So the oxygen will deprotonate the hydrogen, and it will gain an extra proton. So, and usually when you cleave it through alpha cleavage, it should look like that. You should get something like that. Okay, so this is McLafferty rearrangement. Okay, anyone confused? Yeah. Where the gamma carbon is?
Yeah.
It's always going to be the third carbon away from the original carbon. So this is your carbonyl carbon, and from that carbonyl carbon, 1 carbon away is going to be always alpha, 2 is beta. Yeah. Yeah. The third carbon away is always going to be gamma. Did you have a question? No. If you have this shown, like, and then they see this, they'll know what you're doing. Yeah. You don't have to write McLafferty rearrangement or anything. Okay. So looking back, as a fragment of 44. Is it a double bond? I don't. Yeah. Okay. So B is the enol version, but this is the exact same thing as that. So this could be tautomerized into looking like this. And I forgot where the concentration is. Yeah. This should get you 43 because you have 2 carbons. That's 24. There's 2 H's right here. So 3, 4. I think there's a positive charge on one of these. 3, and then 16. There's a positive charge. Yeah. Yeah, that should get you 44. Okay. But yeah, like it's just trial and error. You kind of have to mess with it, and you have to count a lot. I believe you're allowed to use a calculator also on this exam just for that, just for counting. But yeah, it's not very clear. There's no like direct pathway you have to go to. Okay. All right. Any questions on that? Okay. So we're gonna do this synthesis problem. I think that's the last question. So, okay, so just looking at this problem, there's going to be a lot of steps. Hopefully you'll recognize the reagents. So PBr3, that usually turns OH into bromine, and Mg with bromine, that's a Grignard reagent. And then it tells you that B is a ketone. And that, so anytime MgBr reacts with ketone, that will eventually make it into some type of tertiary alcohol. And then the H3O plus, that's just proper workup. That just makes the O minus into a OH. And then it tells you that you have a OL right here. That means there's going to be some type of alcohol at the very end. And then from A to B, this is a strong acid. It's sodium chromate. Okay, so that means you need an acid, an alcohol, and then it'll be turned into some type of acid. So, give me one second. So, to start with A, it tells you it's like a optically active alcohol. Honestly, no idea what that means. It's probably just an alcohol. So from A to B, it's a strong reagent. Okay, so strong usually turns into, you have an alcohol turning into a carboxylic acid. Okay, so that's B, C, and then D. So I would start off with the end product, what you're given, 3,4, that should be dimethyl hexanol. So that should look like, so draw your hexane first. 1, 2, 3, 4, 5, 6. And then on third and fourth carbon, there's a methyl groups. And on the third carbon, there's also an alcohol. Okay? So from here to here, it's PBr3. And then from here to here, there's, I think I'm missing a step actually. Yeah. And then Mg, and then ether is just a solvent, you can ignore that. And then at the end, you have the ketone. Now, it just says a ketone, but it doesn't tell you exactly how many carbons are on each side. And that's why this comes into play. When you draw both your compound A and your ketone, they should match up, and they should give you enough like carbons to react towards that. Okay, so we're gonna make that your ketone. So we have 1, 2, 3, 4 carbons right here. So we're gonna use 3 carbons here. Okay, so this first step will turn alcohol into bromine. That bromine will undergo MgBr. So MgBr will just be right next to it. Okay, so anytime you have MgBr, that whatever is right next to it, that's your nucleophile. So the ethyl is what you're attacking right here. Because there's a partial positive here, there's a partial negative here. So when you open it up, it looks like this. So that carbon, drawing a bond to that carbon. I don't think I drew this correctly. Let's just see where it goes. Okay. So we're missing a methyl, and this should be right here. Okay, I think that should fix it. This is the same thing as that, it's just flipped over. Okay. But, like I only knew what to start with compound A because I've seen ahead, but you kind of have to mess with it and mess with the carbons. You have to count how many carbons you have in your end product, and you see that there's a tertiary alcohol that like confirms that when a granular attacks a ketone, it's going to form a tertiary alcohol. And then these methyl groups, you have to add on, like one of the methyl groups you have to add on in your original product. And then the other methyl group, this came from, so that's your first methyl group and this is your second methyl group. The one's right here. Okay? And then this area right here, that's why we had 2 extra carbons on that. Okay? Okay. Any questions? anytime you react with strong or weak, for a secondary alcohol, you'll always get a ketone. Primary alcohols, oh, I see. Okay, I didn't see that. Okay, so if B is a ketone, then that changes things. Okay, let's move up here. So okay, so maybe it's like that.
Yeah.
So this will eventually turn into a bromine. And MGBR will attack that, and then this will attack. So when you oxidize this for to get here, yeah, you should get a ketone that looks like this. Okay, and then that you can use it for the other side. Okay. Yeah, you should get the same thing though. Okay. Does anyone have questions on the rest of this quiz or any part of it? Okay. If not, I'm gonna get started on NMR. Okay. I know that's not on your quiz, but it's very important for the exam at least. Okay. So let me create a new tab. Okay. So NMR, it's not easy. It does take a while to get used to. It's just like IR in terms of knowing values, but there's a lot of steps to it. So the first thing. So the first thing you should look at is unique signals. So what that means is, so for instance, let's say I have this, okay? So I have 2 hydrogens here, 3 here, and then 3 here, okay? So I have 3 different sets of hydrogens, okay? And we're gonna label them as A, B, and C, okay? So 3 different unique signals means on our graph, there's going to be 3 different peaks, okay? Now, it doesn't look like that, but I'm just telling you, like, the amount of peaks that you see on your graph, that tells you the amount of unique hydrogens on your graph. So let's say you see this, for example. Now, these 3 peaks are the same thing as these 3 peaks. And then these 2 are the exact same, because there's a line of symmetry and they're not unique. Okay, so on your graph, you should only see 2 peaks. Okay, so that's what unique signals are. So something called multiplicity. So let's use that example again. So these 2 hydrogens are neighboring 3 other hydrogens. Okay, so I'll use red for the number of hydrogens, 3, and then blue for the number of neighboring. So these 2 hydrogens are next to 3 other hydrogens. So the formula is n plus 1, where n is your neighboring hydrogens. Okay? So in this case, it's 3 plus 1 equals 4. A 4 multiplicity is called a quartet. Okay, and this multiplicity is like how many peaks you'll get. So on your graph for this set of hydrogens, it should look like this. Okay. For this methyl hydrogens, it's neighboring 2. So 2 plus 1 equals 3, and 3 is called a triplet. And triplet will look like this. Okay. And then let's go back to this. So again, there's 3 here. And then how many hydrogens is it neighboring? 0, right? So you're looking at this carbon here. There's 0 hydrogens on that, so it's going to be 0 plus 1 equals 1, and that's called a singlet. Okay, so it should just look like that. Okay, so if we were to make a graph, which you don't have to, usually you go backwards. You, like all of these, you're going backwards. You're using graphs to make your compound. Okay, so on your exam, there's going to be certain problems where you have to use both, like all 3, mass spec, NMR, and IR. So in this case, there's a singlet, there's a triplet, and a quartet. Okay. For now, I'm just gonna draw them wherever, but it does matter where they go. Okay. So this is called multiplicity. There's 3 peaks here, 1 peak here, and 4 peaks here. So get in the habit of saying triplet, singlet, and a quartet. So this is a triplet, singlet, and a quartet. Okay? So when they ask for what is the multiplicity of, these hydrogens, your answer would be a quartet. And then for these, it's going to be a triplet. For this, it's going to be a singlet. So that's multiplicity, and this is unique signals. So the unique signals here, again, is 3, because there's 3 peaks. And also they will tell you how many hydrogens are being resonated on that peak. And I don't mean resonance in the sense that we always use. Resonance in this case just means like how it's spinning and how it goes through the machine. So for the 3 peak, that's our 3H. So for the 1, again, we have 3 hydrogens, and for the quartet, we have 2 hydrogens. Okay? Alright. Now, location is what you typically have to memorize at the beginning. And, there's charts, and obviously on your PowerPoint, and this is by ppm. Now, the main ones that you should probably know is any of the CH3, CH2, and CH, and it goes in this direction, by the way. It's around like 1.9, or hold on, let me get the exact numbers. Sorry, 0.9. So this is 0.9, 1.2, and 1.7. And these are like rough numbers. It's gonna like go up or down based on like the neighboring groups. So yeah, anytime you have like methyl, ethyl, propyl, like these are the values where you're gonna see it. After that, I would know from 3 to 4 is ether, and from 3.5 to 4.5 is ester. Okay? And then a huge important one is 7 to 8. This is any hydrogens on an aromatic ring, usually a benzene ring. And yeah, usually if you see hydrogens here, this also tells you that, okay, it's going to be a benzene ring. Okay? So NMR can also help you identify functional groups in your compound. And then 9 to 10 is aldehyde. And then I think it's 11 to 12 is carboxylic acid. And then alcohol is kind of weird. Alcohol is like all the way anywhere from 2 all the way to 5. Okay? Let me see what else is important. So chemical shifts is just anytime there's electron withdrawing groups next to methyl ethyl, like they're gonna shift either downfield or upfield. For example, we both have methyls here, but this methyl and this methyl are not on the same ppm value. So this one is closer to the carbonyl, and that's electron donating. Sorry, not electron donating. It's going to be like, it's going to require electrons, while this is going to give off electrons. Okay, so the hydrogen's closer to the atom that's more electronegative is going to have a more shielding effect. Sorry, de-shielding effect. So it's going to be more downfield. So if we were to look at a graph, and they're both singlets, so we're going to draw one peak. This is, we'll just call this A, and we'll call this B. A will be right here, and B will be right here. Okay, even though they're both methyls, even though they're both CH3, that should be 0.9. B could be like 0.8, and A could be like 4. Okay, so like again, like these numbers aren't exact because everything gets de-shielded or shielded by something else on the compound. Yeah. Yeah, it's pulling those electrons. Yeah. All right. Any questions on everything that we covered so far on unique signals, multiplicity, and the location, and shielding and de-shielding? Okay. And then just like IR, the fingerprint region, there's also something called TMS. That's just a benchmark value of 0. It's not really important. The only time that might show up is in a ranking question, and they could, ask ranking also for NMR, where TMS is one of them. Okay. So yeah, and then you guys know the number above each peak is the number of hydrogens actually on that resonance. Okay. So before, the first thing you have to do, or you should do for NMR, is find out the degrees of unsaturation, because that will tell you how many double bonds and carbonyls, or if there's a benzene ring on it. So just to review, it's 2 times carbons plus 2, and then minus hydrogens, minus halogens, and then plus nitrogens, and then all divided by 2. Okay, so every time I do NMR, this is the first thing I do, because it tells me right off the bat. Usually if it's exactly 4, that means there's going to be a benzene ring. If it's 2, that means there's going to be 2 carbonyls. So 2 means, or 1 means any carbonyl. Yeah, so any of the carbonyls. Okay? And then you guys know about the n+1 rule for the neighboring. Okay, so yeah, so let's look at some patterns that you'll see on the graph. You'll pretty much like all of these patterns is to like save time. So the most common one is the ethyl one. So ethyl looks like this. Now there's 2 hydrogens here and 3 here, and neighboring, it's going to be 3 + 1, 4, and then 2 + 1, 3. So this is going to be a quartet, and this is going to be a triplet. Okay, so what that should look like is now the CH2 that's going to be more deshielded. So you're always going to have a quartet here and a triplet right here. So this is your 3H and this is your 2H. Okay. So this goes over there and that goes over here. Now if you see this in your NMR graph, just automatically think it's some type of ethyl in my compound. Okay? So that's one pattern. Isopropyl is another pattern, where you have a single hydrogen here, 3H here, 3H here. Anytime it splits off into this, this 3H and this 3H are the exact same thing. So it gives off the same peak. So 3 + 3, that's 6, and then 6 + 1 = 7. Anything above 4, so 5 and above, we just call that a multiplet. We don't call it, septet or whatever. So, but you still have to look for 7. Okay, so it looks like that, and then all 6 of these hydrogens are bouncing off on this single hydrogen. So that's 1 + 1 = 2, a doublet. And then that should look like this. Okay. Because it's they give off the same frequency. They're symmetrical. Okay. Yeah, and then this is right here because 1 + 1 is 2, and that's a doublet. Okay, and then lastly, terbutyl. So all 3 of these are the exact same thing. And then there's no neighboring, so that's 0 + 1, so that's going to be a singlet. Singlet, and then that's 9 + 1, that's 10. So it's going to look like this. So you're going to have a single peak, and this is going to say 9H, and then and then you won't have like a 10 here because there's no hydrogen there. There's no peaks for just 0 hydrogens. Okay? So to summarize, you have your ethyl here, your isopropyl here, and your terbutyl here, T-butyl. Okay. So there's also something called complex splitting, and this will probably be the last thing we talk about. So in cases like these, when you're counting unique signals, there's actually 3. Even though these 2 hydrogens are coming from the same carbon, they're different because they're bouncing off on like each other and HA. Okay, and the term for all of these, the multiplicity rather, it's called. So you have to look at HA. So when you're looking at HA, you have to look at HB + 1 and HC + 1. So we call that a doublet of a doublet. Okay, so all of these are going to be doublet of a doublet. Okay, same for here, and same for here. Okay, and this is complex splitting. I don't think they should test you on it because it is very hard. The only time it might show up is like during like a ranking question when they ask you to like they'll give you 5 molecules and they'll give you like they'll tell you like count like number 1 would be the most unique signals. Okay, so you have to count like every unique signal. For example, like that would only have 1 unique signal. Like all 4 of these are the exact same. So that's 1, and then another one would be like that. So there's, or not that. Actually, yeah. Like a bromine here. Now that would be 2, and then 3. So that would be 2 unique signals, and then if we were to do the bromine here, that would be, and then I guess an OH right here. So now we have 1 here, 1 there, and then 3 here. So that's 3 unique signals. So stuff like this you have to count and then you have to rank them based on how many signals there are. Okay? Let me see if there's anything else that I'm missing.